Hello, it's Keith here, and this is lesson 4 of my arm thumb assembly programming tutorials. And today we're going to be covering the stack. We're going to be looking at push and pop. We're going to be looking at how branch and link works and how we can use the stack for storing return addresses. And we're also going to just complete things and look at SWI. Now, if you already know ARM and you're confident with it, you're probably not going to learn a whole lot from this lesson because not much has changed, and I actually covered the basics of how things had changed in last time's lesson. This is really more for a recap for people who don't really understand ARM that well or haven't looked at the regular ARM and are just starting on ARM thumb, if that's you. I really wanted these lessons to be a complete coverage of all of the content of the ARM thumb instruction set, and so this time I'm going into these in the usual detail I did with the regular ARM, but I think there's not much has changed, so you may not need this lesson if you're confident with your ARM programming. Anyway, today we're going to be discussing the stack. We're going to be seeing various examples of pushing and popping items on the stack, and we're going to discuss what stacks are because, as I say, this is done for completeness, so if you don't know what a stack is, you will do soon. Anyway, let's go over to the blackboard and let's have a look at the idea of a stack. So, what is a stack? Well, I always compare the stack to being a bit like an in tray for your items. So if you imagine that that's an in tray, and if you imagine it's also square and properly drawn, which clearly that isn't, and we want to store some items we're working on, maybe people keep giving us work to do and we can't deal with it all in one go. So someone gives us an item 1, and so we can't deal with it right now, so we put it onto the bottom of our in tray. Another item comes in, item 2, and that also goes into our in tray. A third item comes in, item 3, and now our in tray is full. So we're going to have to start dealing with those items. Well, when we take them off in the reverse order. So we take an item off and item 3 has gone. We take another item, there goes item 2. And finally, the last item we take off our stack, our in tray, is item 1. The point I'm making is the items come off the stack in the reverse order they went on. It's known as a last in, first out stack. So that's the way stacks typically work. And the reason I compare them to an in tray when we're busy is they're usually used for temporary storage of items. So that's why that comparison, I think, works especially well. So we're going to be seeing this in examples in our code. Let's get over to our code and let's see what examples we've got. So the first example we're going to be looking at is a simple example of pushing items onto the stack, and we'll be able to see those items on the stack. Now, the real major change, of course, with ARM thumb is before we were using some various loading and storing multiple commands to do our stack manipulation. Well, those commands have been heavily pared down now, so now we have a dedicated push and pop command to work with the stack register, and this will allow us to work with the stack in roughly the same way as we did before. We can still use the same combinations of registers to push and pull from the stack, but the commands are now slightly different. So let's have a look at this example in action and see how this affects our stack. So what have we done? Well, we've loaded a value called test value here, and if we just find that, there's our test value. It's got to be lurking around here somewhere. Here it is. So here's our test value, and it's FFEEDDCC. So that's the item we're using as a test here, and you can see it's loaded into R0 just here. So we've loaded that test value, and then we've used this push command to push R0 onto our stack. Now, we've got this function called show stack plus R0, which is just a little piece of test code which shows the contents of some of our registers here. It shows the R0 register, the stack pointer register, and it shows the contents of the stack. Now, this is the stack before we did any pushes at all. So that's what we started with. We then pushed 4 bytes onto the stack with this push command. So the stack pointer went down in memory. Every time we push, the stack actually goes down in memory. So if this was our stack and it started at, say, FFFF, every push to the stack would go up in memory, and eventually maybe we'd get to F000 there. That's just an example, of course. Those aren't real memory addresses that we would use on this system, but as I say, that's the concept. We're going down in memory every time we push onto the stack. And you can see that here. We have started with FFDC here. We've pushed 4 bytes and we've ended up at FFD8, which is 4 lower than our starting stack position. And our item here has now been pushed onto the stack here, but the bytes have become reversed because we're on a little endian system here. So those bytes have been pushed onto the stack there. We've actually loaded 0 into R0 here, and so when we show the contents of the registers on the stack, R0 has now been reset. Now what we did after that is we popped the value back into R0 off the stack, and we showed the contents of the stack again. R0 has now got its value back, and you can actually see that the value on the stack has disappeared, although that isn't actually a function of the CPU. The reason it's disappeared is this is a software monitor function, and it's called a subroutine to show a dump of the memory, and that call has actually wiped out parts of the stack above the previous stack pointer. The stack pointer is back exactly where it was before we did any of our pushes, and so the spare memory has been used by my monitor function and has been cleared. So as I say, it's not cleared by the pop command, it's being cleared by my test code. So that's just something to bear in mind there. So that's how we can back up and restore a single item in just one iteration. What we're going to do now is we're going to do basically what I showed before with my in-tray example. We're going to push multiple items on the stack, and then we're going to pop them off the stack in the reverse order. So let's check that out. Okay, so we've loaded our test value here, and we've shown the starting contents of the stack, and you can see that just here. There's empty stack here, nothing on it of any particular interest. We've then pushed R0 onto the stack, and we've loaded a second test value, which I believe is 44332211, and we've then shown the stack again, and then we've pushed that second test value onto the stack. Well, let's take a look at that. So here we have our FFEEDDCC, that's our first test value. The stack contained nothing. We've then pushed that test value onto the stack here, and we've loaded our second test value into R0. We've then pushed our second test value onto the stack. You can see it there again in little Indian. And of course our stack pointer each time is going down by 4 there, and that has got us to this position here where we've loaded a 0 into R0 here, and you can see R0 has become blanked. Now we're now in a situation where we've got 2 values onto the stack, and our R0 register is back to 0. So what we can do now is we can then pop those items off the stack and see how they come back to us and how the stack is affected. Okay, so what we've done here is we've then popped the value off the stack, and that's gone into R0, and R0 has got its 44332211 back. You can see, as I said before, my test function has cleared that value off the stack, but our FFEEDDCC is still on the stack. That's the first item we pushed onto the stack. Because it's a last in first out, it's the second item we pop off the stack, and we pop that second item off the stack here, and you can see FFEEDDCC has been restored into R0 here, and the stack is now clear, and our stack pointer now points to the value at the end that it did at the start. So we're back in the exact same position we were when we began, and that is what we want to do. We want to push and pop the same amount of items so that when our subroutines end, everything's back the way that it was when they began. That's important because our subroutines need to leave things the way they were, and also if we are popping off the return address from the stack, well, if the stack isn't back the way it started, then we're going to have a bad time, we're going to make a mess. Now what we're going to do next is we're going to take a look at pushing multiple items. Now we can do this in the exact same way as we could with the normal ARM. We can specify a range of items, in this case R0 to R1, but of course we could do R0 to R3, and that would do R0, R1, R2 and R3. We can also do comma lists. We can specify a register, comma another register, and we can of course do combinations. We could do R0, comma R2 and then R3 to R5. We can do that. We just specify them accordingly. Now hopefully what's happening here isn't particularly amazing and surprising to you. Hopefully you understand. We've basically loaded 2 test values here. We've pushed them both onto the stack. We've cleared those values, and then we've restored the 2 values in one go here. And you can see here that we've taken these values here, we've pushed them onto the stack. Here they are, they're on the stack, and then we've restored those 2 values here. Now just for clarity, the order that we specify the registers here won't actually matter. If we put these in the opposite order, They will still be restored in the same way. It doesn't make any difference here. The R0 here and the R0 here are the same, because the order in this list and how we specify them with commas and hyphens and things doesn't actually affect the way they end up in the bytecode and the way the processor interprets them. However, what we can do is we can put multiple pop commands of single items here, and we can reverse the order in that way. For example, if we do this now, if for clarity we just change this here and we do R0 and R1 here, and we just specify them here. Now this time we're pushing R1 and R0 onto the stack, and we're popping R1 and R0 off the stack. But because, as I say, it's a last in first out system, we're actually going to end up flipping them over. We've pushed R0 and then R1 onto the stack here, but we've popped R1 and R0 in the opposite order. So R1 has been popped first, and so that's got the original value of R0, and R0 now has the original value of R1, as you can see just there. So yeah, if we want to reverse the order intentionally, we can use multiple pop commands, but the order of a combined command does not have any effect on the way they're popped. If the registers were different, of course, they would have an effect. If we were pushing R1 and R2 but popping R3 and R4, for example. Okay. Now that's the push and the pop command, and most of the commands for working with multiple registers no longer exist, but we do still have STMIA and LDMIA, and these will store or load multiple registers from the address in a single register. So let's fire this up and let's take a look. So here we're going to store the registers specified R0 and R1 into the address in R7, and we will update R7. The exclamation mark specifies we're updating, but actually we can't specify this command without that exclamation mark in this case. And here we're going to load the values back. So here we've got a value for R0 here, FFEEDDCC, we've seen that quite a bit, and R1 44332211, and here is our test memory range. So we're then going to store these test values, and we're going to 0 and set to 1 R0 and R1 here, and we can see that has happened just here. And this STMIA command has stored our two registers at that memory address here. Now you can see here we've stored R0 first, and then we've stored R1 second, and these are in ascending order. They're going up in memory rather than down in memory like the push and pop command. So that's where we've stored the values. We then cleared them here, and then we are using a LDR command to restore the value of multitest, the address that we're reading from, and then we read them back from that address here. And you can see here FFEEDDCC and 44332211 have been restored. Of course, the memory range isn't affected, and as I said before, the stack actually wouldn't have been affected as either. It's just because of my test code that was altering the stack. But these commands are not really a push and a pop. They of course have a similar function in some ways, but they aren't specifically designed for using as a stack. They're more intended for bulk reading or writing of data, which could be quite handy if you're, for example, reading bitmap data for sprites, if you want a very fast sprite routine. So those are still available to us. Those are the only load and store multiple commands that are available to us on the ARM thumb, but you know, they're there, so we might want to use them. So now what we're going to do is we're going to take a look at branch and link. Now branch and link hasn't really changed since the ARM, so again, if you know your ARM, you probably don't need to know this, but if you're not so familiar with the ARM, or if you're learning all of this in a rush, then it's worth recapping because it's so important. So basically, the link register is the return address when we do a branch and link. A branch is like a jump. It's intended for us to not return, just to skip over a section of code. Branch and link is like a call command or a go sub, if you're familiar with those kind of commands in other languages. So branch and link is going to go to this subroutine called branch and link test. This subroutine, it just adds 1 to R0, shows the current status of the link register, and then it effectively returns. Moving the link register into the program counter is putting the return address as the next running command. The program counter is the running command, and the link register is set to the next command when we do a branch and link. So let's turn this example on and let's check it out. Okay. So what have we done? Well, we've loaded R0 with a 0, and then we've run branch and link test a first time. So that has added 1 to R0, and then it's shown the contents of the link register. So here we've got a situation where R0 contains a 1, and our link register contains 2, a load of zeros, and then D8. And D8 will be this line here after the first branch and link. We've then done a second branch and link to branch and link test. This has increased R0 to a 2, and the link register now equals DF. And the reason it equals DF is we've effectively moved a few bytes along with our return address, because we're now running a second branch and link. So the first one returned to this line, and the second one returns to this line. So the link register has changed accordingly. So that's what we've done there. We're now going to do a test called nested BL test good. Now this is a properly working example. Now this itself is a branch and link, and within this we're branching and linking to other branch and link subroutines. Now the problem we've got here is when we branch and link here, this is going to change the link register, and if the link register changes, we will have no way to return back to this line here after this branch and link to nested BL test good. So how are we going to do this? Well, the easiest way is to push the link register onto the stack at the start of our subroutine, do whatever our subroutine needs to do, and then pop the program counter off the stack at the end of the subroutine, effectively popping the return address into the program counter because we pushed the link address, which was the returner counter. So this routine will now run. And what will happen here is we've run branch and link test twice. So this effectively adds 1 each time. And you can see here, 1 has been added twice, and our link register has gone up again at the end of the code here. And then what we've done is we've moved not, and we've flipped all of the bits of R0 here, and then we've effectively returned. Finally here we show the end situation after our code. And you can see here that that has indeed worked, because the R0 has had all of its bits flipped here, and then we've returned here. And we can just check that if we just get our calculator up here and we put in FFFB here. So if we just do this, FFFB here, and then we flip the bits, you can see the result is indeed 0004, which was the original value we had there. So there we go. So our subroutine has worked okay. It's flipped the bits as we expected with this move not, and then it's successfully returned with the pop here. Now that's what happens if we correctly back up our link register for when we need to return. Well, here we've got a bad subroutine here, which is running some subroutines, but it's failing to do anything to protect that link register. So when it tries to return here, that link register is going to be incorrect. So let's be a little bit mischievous and let's test this incorrect version and see what happens. And what will happen will entirely depend on the system we try and run it on. Well, first what we've done is we've added hexadecimal 10 to R0, and this has of course worked. So R0 has changed. We've then done our branch and link test, the first one. This has added 1 and shown the results. So R0 now equals hexadecimal 13, which has worked fine. The second subroutine of course also works fine, and this changes R0 to 14. But then when we try and return, well, our link register has been altered by these 2 branch and link commands here. So when we return, well, we're not returning to the right place, and our program has apparently crashed. There's no more code, nothing else to see. So we need to make sure that we protect our link register when we're doing nested subroutines. We don't need to if we're just doing a single routine, but to be honest, if you're not sure, the best thing to do is just push the link register at the start of your sub and pop the program counter at the end of one, and you will have no problems. Now, the last one we're going to be covering, just for completeness, is the software interrupt. Now, this doesn't really have any effect on this system, but basically software interrupts are operating system calls, you could call them. They're very much like traps on the 68000, and these do still exist on the ARM thumb, although with a more limited range. So basically what these do will entirely depend on the system you're programming for. On the Nintendo DS, I don't believe they really have any function. I've never had to use them, at least, but maybe there's some case where you would. Anyway, they're more useful on RISC OS. RISC OS used them for system calls to make the operating system do things for us, as I say, very much like traps do on the 68000 system. But the RISC OS doesn't use ARM thumb, I believe, so we're not covering it here. But anyway, as I say, the SWI does indeed exist in ARM thumb, so if you have cases you need that, it is still available to you. Anyway, there we go. That's all we're going to be covering today. As I say, always go to my website. You can download the build scripts and the source code for today's example with all of the others examples, and you should definitely download them and have a play with them yourself and get to grips with it all. Anyway, if you like what you've seen and you want more ARM programming help, you can get my book and help support my content. My book's called Learn Multi-Platform Assembly with Chibi Alchemist. It covers Z80, 6502, 68000, 8086 and ARM. It's only full ARM, it's not ARM thumb. I apologise, but if this book's a success, I will write another book and I will make a book on ARM thumb one day. So anyway, if you want to support my content and have a look at some other assembly languages other than ARM, please take a look at that. Anyway, I hope you've enjoyed this today. Thanks for watching and goodbye.